Yes, it started.
Yes. Good evening, everyone. Welcome you all for this today's session. So for today's session, we have Dr. Sridhar Palla. He is an assistant professor in chemical engineering at IIPE Vishakhapatnam, specializing in carbon capture, hydrogen storage, and sustainable energy solutions. His research combines experimental and theoretical approaches, focusing on advanced materials like metal organic frameworks, multi-scale modeling, and machine learning. Dr. Palla's work addresses critical challenges in energy efficiency and contributes to India's net zero goals. A prolific researcher with numerous high impact publications, he is dedicated to bridging academia and industry for sustainable innovations. Dr. Sridhar, you can take the place.
Good evening, everyone, and thank you, Dr. Nalinkant and Dr. Rajesh, for inviting me to this ATAL faculty development program. So, in as Dr. Nalinkant mentioned, our research group at IIPE is currently working on various energy solutions. So, industries all around India and the world currently facing this energy efficiency problems due to the switching from our fossil fuels to the renewable energy, and at the same time there is strong opposition regarding emissions of the carbon. It could be the CO2 emissions or methane emissions, and production of this green hydrogen. There is lot of various aspects that are going on, and we have been working on finding efficient solutions for these aspects. So in today's lecture, I will be talking about how can we use the advanced machine learning tools, and how can we apply these tools in finding the energy solutions. I will be showing a couple of two case studies where we have worked on such as the hydrogen storage, and also uh, finding the bio-oil yield, that is biomass pyrolysis study. So what I'm trying to say here, I will introduce you to the AIML with a few basics, then I will switch to the uh, energy applications. How can we use our AIML tools for the energy solutions? So instead of going into the technical details how these algorithms works and everything, most of the people who are working in this domain, in energy domain, this talk will be very useful for you. How can you model any energy system that you are currently working on, or any industry that your work is related to? What are the inputs that you need, and what are the parameters that required to complete your model, and how it would be more accurate to predict. It could be the efficiency or productivity, any of the output that you are looking at. Okay, so by end of this lecture you will get some basic idea of how can we use this ML tools for modeling the energy systems. So moving into this, couple of fundamentals first. There is this term called model we use most of the time in research, and are in our standard textbooks. We have multiple models like idle gas law, and also we use this Newton's laws as our fundamental models. We solve those equations and try to figure it out, what are the physical characteristics, whether it could be the movement of the body, or it could be the pressure, temperature, and volume of any gaseous system. uh, so the model is a term that we use to represent any physical system that represented by using the mathematical equations. Okay, then we call that as a model. So the models are mostly based on the approximations what we make. The natural system we try to replicate on we try to solve that system on computer. We have a couple of numerical methods. We can use those numerical methods and solve those equations. Those equations gives us result. However, these results are not as accurate as our experimental true values that we get. So we have multiple approximations. However, we try to uh, find accurate results. How can we approach the more accurate results? It depends on what type of method, what algorithm we are using, and how we can mitigate the errors in this process. So as I mentioned, there are several models in our standard textbooks, and most of the mechanical and chemical engineers can relate with the examples given over here, like transport equations. Just give me a minute. Um, yeah. Yeah. So, as I mentioned, we have conservation laws like mass, momentum, and species balance equations, and also the energy balance equations. They are very standard models we have to understand the physics of any engineering, chemical engineering systems like reactors, and also we have adsorber systems. Uh, then there are several non-ideal activity coefficient models in thermodynamics we have, and also the chemical kinetics. So all these equations that we find in our textbooks, they are also called the models. So generally the model requires some inputs. What is the information that we are feeding to the model, and what is the output we are getting out of it? So what is the result we are expecting, or what we would like to predict? At the same time, these models, they depend on several parameters. It could be the environmental variables around, and what are the effects that we can find by building this model. For example, there is one certain kind of reaction that we are conducting in India, may or may not work in some western part of the world due to the changes in the ambient conditions. Okay, if we only consider only the input and the output by neglecting the system parameters, so it we always we need to consider this system parameters which would affect the output. Okay, so that could make our model better and more accurate. So this is very simple graphic. This would help us in understanding how to build a model, perfect model. Generally, first we need to understand what is the problem we are trying to solve. It could be any physical system, any engineering system. We need to select that problem, and we need to understand that problem first and start building the model. I will show how to build it in the coming few slides. Once we have a model with us, then we can compare our model with we have several numerical techniques that we can use to solve those models. If we have linear algebraic system, or nonlinear equations, or partial differential equations, ordinary differential equations, we can either use analytical techniques or numerical methods to solve them. Then we can compare our result with experiments that tells us whether your model is working perfectly or not. And at the same time, we can get the error, how much error that we are obtaining when we compare our model with the experiment. So this will help us to improve the model, and based on the result we can either come back into this same loop and start modifying the model and again running the simulations. So after doing multiple iterations, we will end up with a more accurate and perfect model which could predict the experimental result accurately. So once that is done, we can document that results and publish it. This is how generally we build our models and apply that to the real systems, and then we finally deploy it. So based on this introduction, the main motivation behind building a model uh, all the time we may or may not need these models, but what are the cases when do we need these mathematical models? First thing that comes into the mind from industry perspective is the economics. Okay, it is inexpensive to build the models if you have one a computer or computational power, or if your calculations are highly expensive, you need a servers. So what I'm trying to say here is we can recreate the plant, the industry, or plant on the computer, and we can simulate that industry and obtain certain results that we are expecting. So this will save a lot of material, and at the same time the time that is going into this process. So this economics actually plays a major role. For example, if we would like to conduct some certain type of reaction in the laboratory, for example, A plus B gives the C. We need to buy A and B and to get and also one reactor, and whichever the tools that we required to get the C. So this we will repeat till we get required are the desired amount of the C and the conversion, and we will still repeat this process. So it will consume a lot of material, okay, and also the manpower. So in that case, if we could build a model that could predict what is the amount of the C that is producing, how much amount of the A and B that we feed into the system, so that will help us from the economic point of view. At the same time, there is a operation challenges we also face from experiments or in industrial scale operations. Alternative techniques can be explored to analyze possibilities to enhance the process performance and also the yield. In some cases, we may need to perform certain operations at extreme conditions. It could be high temperatures or the high pressures or some certain nuclear reactions. Instead of building or simulating the lab at those conditions, we can build a model that could predict the result at the required operating conditions. So that is also one of the advantages. And scale up, let's assume that there is one oil refinery where they would like to try some new fuel to get whether different from the refinery, whether they are getting different cuts of the grades of fuel, whether they are getting or not. When they would like to try some new distillation column or new reactor, they don't need to replace that particular unit, the large scale units, with the new one to study whether it is working fine or not. Instead of that, there are some very good tools like Aspen simulation tools that are available, and these tools needs a mathematical models which will be solved on computer screen itself, and then it can give us the result. So it saves a lot of money, and it saves a lot of time, and it simplifies whole process of this experimentation that is going on the lab scale or pilot scale or the industrial scale. So that is the basic motivation behind building these models. So now the question is how to build these complex models for these complex processes. First question we need to ask is whether your system really require a model or not. There are a lot of complex systems where conducting the experiment would be very difficult at those operating conditions, as I mentioned. And there are few systems where in our UZ labs, undergrad labs itself, we can build those equipments and infrastructure and solve that particular problem we are facing. So in those cases, we need to ask whether it is experiments are very simple and easy to conduct, then it is better to go for that experimental study. Otherwise, then we can use these models for the complex systems, and which can be cannot be conducted in the lab scale. Then we need to ask another question, that what are the effects of the simulation? When we are building a model, you need to understand what are the effects of surroundings. It could be the temperatures or the pressures that we are operating in the real time. I mean, in the real industry operating conditions, whether we are replicating those in the lab scale or not. If those effects are not considering, then we don't get accurate result as that industry is producing. Then we need to find what are the input data, what are the input data that is available with us when one industry asked you to develop a model. First thing you need to ask, what is the information they already have. Nowadays most of our refineries are most of the industries, they are some they have been working for decades, so they have this databases where the input information and what is the result, what is the output they are getting, they have large databases available. So they can provide you, in case if they are providing that information, what type of information they are providing you for to model this. Then first thing you need to question what is the output you are trying to find, whether it could be efficiency or whether it could be the productivity of that particular operation, or what type of output you are expecting from the model, so that you can build your model based on the input and the output. Then based on this, both what type of output you are getting from what is the input we are providing, algorithm can be developed. There are multiple algorithms, multiple machine learning algorithms nowadays available. I will show a few in today's lecture. Then you can decide whichever is better fit for your system. Okay, based on that model, based on that only we can select the best algorithm for accurate prediction. As I mentioned in one of the graphic, that system variables and the operating conditions should be considered. Okay, if we are neglecting the system variables and operating conditions, there are high chances the accuracy will be less. Okay, because every time when the student from mathematics or the students from undergrad students, they come to us for the project. When we provide the data, they look data of any engineering system or any reactor, they look into data as a numbers, numerical data. Okay, they don't understand what exactly happening inside the reactor. If they don't understand the effects of the surroundings and the effects of other parameters, the system variables, then there is high chances that model may predict very bad result we will predict from that model. So I always recommend to include these system variables and the operating conditions also in your model. That improves the accuracy. So always keep in mind before going for this ML based modeling or any numerical modeling in that case. So now the question is, as I have been mentioning multiple times, why should we apply this machine learning to the energy systems? There are multiple cases where we, for example, if multi-scale modeling is a one interesting topic where we have a reactors, or we have these distillations columns in the industry which are in the meter scale, or from it starts from the centimeter to the meter scale, and we have a pilot plants which are in range of this meters. Okay, then we have tools like computational fluid dynamics and to finite element methods are available to solve those particular equipment. Then we have some molecular modeling tools that are available to calculate the properties that are required for material at molecular level. So all these various mathematical techniques that are available all are time consuming, and sometimes they are not accurate. So in, in most of these complex systems, we need one alternative to all these various techniques. That is where the ML plays major role. When we have a information, experimental information already available from either from the industry or from the laboratory, we can use that information to predict the output. That particular model can be trained on the previous information and use it for the future purpose. So that is where the ML comes into the picture. So here we can see whoever already well aware of this machine learning technique, uh, these are couple of basics I would like to cover first, that starting from the machine learning. So whoever new to this machine learning, okay, always remember this. I give this example to the people who starts working in ML with this the graphic as shown over here in the slides. When we throw this bunch of toys to the kid in one box, and we if we ask the kid to arrange the toys in certain order. For example, there is a box contains rectangles, circles, hexagon and the triangles in one box, and if we put four other empty boxes which are labeled as rectangle, circle, hexagon and triangle, and when we show kit that this particular four-sided shape is a rectangle, and this round shape is a circle, and this three-sided shape is triangle, and six-sided shape is hexagon. And if we put each of them in each of their independent respective boxes, then kid will learn from that particular uh, teaching from us. Then later he will start picking each of the shape, and from the labeling that we have done in the first round of sorting, he will put all those shapes in the respective boxes. If the smart kid is very smart, then it will be 100% accurate. He will put all those shapes in their independently, each of them in their own boxes. So this is called a training. Okay, we from the first round of sorting, we have we told that the particular four-sided shape is called the rectangle. That means we are training the kid that put this particular shape in the respective box because it has a four sides. Okay, that is called training. Once we train that kid, next level we cannot throw him into this society, right? We will conduct one test to him. Similarly, we will give some new shapes such as this three-sided triangle and also this round circle. If we give another two toys to that kid, then this kid, what he will do based on his training from this previous step, he will put this triangle in one box, that is in the triangle box, and this round shape in the circle box. Okay, so that is called testing. So any data from now onwards, if you find any data for any system, it could be the labeled data or unlabeled data. Unlabeled data means we are not telling the kit that this four-sided shape is rectangle or this round shape is circle. We will just throw this toys to him and ask him to sort it out. Then what he will do, he will put all the rectangles together, circles together, triangles together, hexagons together. So this particular step is called the training, and the second round of step is called testing. These are the very important steps in developing or building one model, machine learning model. So it could be any random data. Data could be from any physical system. It should follow these two steps and to get the prediction whether the prediction is 100% or not. If he put both of those triangles and the triangle in the triangle box and circle in the circle box, that means your the model is 100% accurate. If he puts those triangle in the rectangle box and the circle in the triangle box, that means your model is not working well. That means the training was bad. Okay, that means the model was very bad. So this is how we build one machine learning model. This works for this theory works for all type of data. However, uh, it will be more complicated based on how your data is. Okay, if your data is very nonlinear and large amount of the data if you have, then it takes more number of the steps to reach the prediction stage. Okay, that also we will look in this in the coming slides. I hope this concept is clear for everyone. Uh, Coming to this definitions of this ML modeling. Okay, machine learning models are nothing but the computer programs. Okay, they are actually designed to find the patterns in the data to make the predictions. Okay, in previous example, the machine learning model that try to find the pattern, that means what are the rectangles pattern, what are the triangle pattern, what is the circle pattern, what is the hexagon pattern. Once the pattern has been found, then it will, when you throw some new triangle into that model, then it will tell you that this is a triangle. Okay, that is how this ML model works. So the data can be different types. It could be the labeled data, that means we are telling the four sides as a rectangle. If you are not telling that four side is a rectangle, that means it is a unlabeled data. Sometimes you will have labeled and the unlabeled data, that is called mixed data sets. So there are several types of algorithms available, okay, to model these data points. It could be the classification based or the regression based, and we conduct the rigorous training to improve the efficiency. And this data scientist, we can similar to this previous example, we can also identify these animal species. If you put multiple pictures to train one model to detect which type of animal is that. Okay, that is also one of the very good example where based on the images of the animals, our algorithm will predict what is the animal. So these are a couple of examples, very basic examples. So now again the question is, okay, we have multiple theoretical models that we developed, like CFD models or molecular simulation models and density functional theory based models. For chemistry people, this might be a very interesting topic. All those various type of theoretical fundamental models are there. Then why we are going for this ML?
So
Uh,
I
but
have one question.
yes, please. Or
Just
should
with
we
the last
wait?
example, just with the last example that you said,
Mm-mm.
if the animal, if you give now one of the animal, it will be able to tell. But what if that animal itself is completely new, or that thing is completely new? Will it be able to predict its futures at least to some extent?
Yes, it depends on how many animal images you are providing it to the algorithm. For example, if you are providing 500 animals, if your new animal image that you are providing it to your algorithm, if your algorithm is highly accurate, then it will tell you what is that animal name. If your animal is from that 500 data points, that means 500 images, then as you mentioned, it will predict close to the animal that you have trained your model. But still it may or it may not be accurate as the new animal. That
But
is a alien data. Yes, please.
but if we give the justification on the accuracy, that can be with some past experience or some insights, that would be okay, isn't it?
Yes, accuracy is depend on whether you have any validation to compare or not. Right. For example, if in labs we do these
Yes.
experiments, we use the experimental data to validate our result. Once my model is trained from the previous information, I will pick one random data point and I will compare with my previous experiment. So that tells us whether my model is predicting well, it is accurate or not. The
Okay.
validation step is
Got
very
it, sir.
important. Yes, yeah. So coming to this topic of requirement for ML models, I have been mentioning multiple times, like handling the complex and nonlinear systems. In all the cases, we may or may not have accurate codes or tools, or we are not confident enough to use them. Then also these ML models are very helpful in predicting based on our previous experimental results or literature that is available. At the same time, processing these large volumes of data, this is very useful for the industries where they have been collecting their everyday industry. They have multiple sensors in the industries that gives a lot of information. That information will be stored. That information can be used to develop one very good model that could predict what is going to happen in the future also. In case if they tune any parameters in their plant, how the efficiency or the output that could change. And to optimize the processes, such as if you would like to optimize one system to get very good energy efficiency, now you need to, if you model that particular system, then if you change any parameters, the efficiency profile you can build. Okay, based on that efficiency profile, you will pick the optimal point where at what parameters you will get that very high efficiency of that system. So that is also very interesting to explore. At the same time, this forecasting and the predictions, most of the industries or R&Ds we use, we build small lab scale setups and we try to forecast how it would work on industrial scales, and what by changing the real-time operating conditions we will provide to that model and check whether it is working fine or not. Then also for the decision making under uncertainty, in case any uncertainty that occurs, what type of decisions to be taken. Then integration of these renewable energy sources. If we start integrating one small setup or the unit into the already existing plants, then how that setup can change the final productivity or outputs. Then any fault detections or the maintenance can also be predicted based on the previous information that model could be trained. So these are only small examples. There are multiple other applications also we can use, and for the machine learning. So based on this introduction, we will see how to build a model and how to apply this for energy systems, and in case if what are the challenges we may face. Okay, so here you can clearly see, although I'm concentrating only on the energy systems, so mostly the renewable energies you can see, either biomass, wind, and turbines, and also the solar power. Always the first step is to collect the information, whatever the available information, either from the reliable sources or from the literature. We need to collect that information first. So the once you have the information, it could be you need to understand whether that information is enough to predict or to predict the result accurately, or you need to collect more number of information. Based on your experience, you can analyze that. From that step, first we need to clean that information. In most of the cases, when we get this raw data in from the real cases, then there is a lot of missing information. For example, if y is predicting on the basis of a, B, C. Okay, from one data point from one particular industry, I got ABC for predicting the Y. From some industry number 2, I got AB, but there is a missing information of the C, but I have Y information. So similarly, when we collected this information from all those hundreds of industries, for example, all over India, if you get A, B, C information to predict Y, that is fine. In case most of the cases we don't get all the input informations for the Y. So that is called missing information. And also in some cases we will get duplicates which are overlapping data points also we will see, and invalid data points also we will see. There are outliers also present which might be some wrong estimations from the sensors, that also we will find. All that information, in case if we are considering without cleaning this data, in those cases what happens, this model that we are building, okay, could be inaccurate, because due to these outliers the model try to deviate towards that side. Okay, So we better remove all these unwanted information like outliers, duplicates, and the missing information that will help in building the better model. So this whole process will be done in pre-processing and also this data analysis. So data analysis will help you in understanding what are the outliers, and it is actually the statistics that we will conduct. We'll try to find mean, mode, and median, and that will help us what are the points which are away from the mean, which are outliers. Once that step is over, then there is a training step. We will select couple of models based on either the literature survey or based on your experience or based on what type of data set you are using. We will pick that model and we will train that model as shown in that multiple shapes example. We will first train it, then we will test them, and then based on the testing we will fix which is the most accurate model, and then we will optimize the parameters, which parameter can predict you the best output. It could be the efficiency or profit or the productivity. Then we will use that model for the real time applications for the future predictions and any forecasting. So these are a couple of steps that are required in building the ML model. So I will quickly cover a few other basics before going into this energy application, such as uh, first, this machine learning model can be classified as supervised and unsupervised. As I already mentioned, in supervised learning, for example, we have multiple input features like x1, x2 up to xp are our inputs. Then we know what is the output we will get if we are using x1, x2 and the xp. Okay, this is called supervised learning. That means we know what is the label. Okay, what is the information that output that we will get if we are using certain inputs. Okay, this is called labeled information, and the technique that we use for this set of data is called supervised learning. In case of missing targets or missing labels, when there is no label for the data, that is called unsupervised learning. Okay, that means x1, x2, xp information will be available, however we are not going to tell what is the output. Okay, so this type of information we call it as a unsupervised. In case if we are using this ML technique for this kind of data is called unsupervised learning. So this supervised learning, we can again classify into this regression and also the classification. That is a very fundamental classification. Whenever we have the information that could predict the continuous values. Okay, these continuous values we observe in our undergrad labs. Mostly we plot x versus y. For example, the salary versus the experience that we have, or the temperature versus the humidity information. In case if we plot how the humidity is changing with respect to temperature, or any feed that is going into this reactor and how it would affect the conversion. So this is a continuous information we will get, and that could get the output. Okay, but in case of this classification, the values will be discrete. There is no continuity we will observe. Okay, in those cases, for example, this is a very good example for us to understand. In our Gmail, we can see these spam mails and also the not spam mails. Okay, the mails sometimes it will auto detect whichever are the spam mails and put them in the spam folder. Okay, for most of the cases, the mails that come from outside your organization, they will be classified as a spam mails and they will put in that folder. Okay, similarly, when we go for this blood test or any test, medical test, also we observe this positive and the negative reports. Based on some analysis, they will classify that information into the positive and the negative. Similarly, we can classify different color balls or different color fruits like red and the blue color. We will classify them based on their quality or For example, if the color is one of the specification of that route, we can use that and we will classify them. So that is the difference between this regression and classification. In case of unsupervised learning, most important point to note down is there won't be any labels. Okay, that means we are not we are telling the model that there is no output information that is available for this. So just consider only the x1, x2, x4 up to xk. Okay, based on that information only we will try to model that particular system. So it receives a data and starts extracting the valuable information based on the data that we are providing. So generally this unsupervised learning has a very good ability to discover the similarities, okay, and the differences in the information. As our first example, where multiple shapes are there, based on their pattern we can classify them as rectangles, squares, triangles, okay, and also the circles. That is one of the way, based on just looking at those shapes we can classify them, okay, although you provide the label or not, okay. And sometimes we have these exploratory data analysis techniques like analyzing the data. If we plot all of them together, then also we can find patterns, okay. There are few statistical techniques available, and dimensionality reduction is one of the unsupervised technique which will be useful in reducing number of features in case any unwanted features are that could be reduced. And also there is this clustering technique which will put all the similar patterns in one cluster, okay. We can by looking or investigating that one element in that cluster, we can name or we can give the label accordingly. So there are a few other examples I will show you, then we can move on. One is the retail marketing. So generally in retail marketing, people try to identify households. It used to be done before this online shopping and everything. People used this shopping corporates, they used to find these households and try to put all those various households in some certain clusters, okay. For example, they consider multiple features like household income, household size, or who is the household and what is his occupation, and at what location generally these houses are they are living in. Okay, all this information they collect and they will try to build one clusters. For example, there is a small family but they are spending more amount, and there is a cluster to like large family, they are spending high amounts. Okay, similarly they can build small clusters and they will try to advertise their products accordingly. So this information is one of the unsupervised learning. So similarly, there is this streaming services example. Most of you are aware of this OTT streamings these days. If we go to this Netflix platform, there we observe these tags like it is a horror movie or the thriller movie or romantic comedy movie. Okay, sometimes we find exactly the same cluster, same movie in that same label. Okay, sometimes there will be some mismatch. Okay, some horror movie will be placed in some thriller or some romantic comedy also. That may happen. That is because of bad model. Okay, so the streaming services generally uses this kind of classification. For example, it will put the customers also in certain clusters based on how many minutes they are watching and what are the how many viewing sessions per week and number of unique shows they are trying to watch, whether they are watching the same show again and again or they are trying to watch some new shows. They collect this information and they will try to put you in that cluster. When you next time open that particular streaming service, you will see those same shows or same pattern you will observe. If you are keep on watching one horror show every day, then you may get the suggestions from that Netflix or any other service, OTT streaming service, the same type of the shows. Okay, that is how it works. Similarly, the health insurance, it is one of another very good example. Okay, the people generally collect this information from us, such as how many visits we had with doctor, or what is the household size, or any chronic conditions per household, and any average age, what is the average age of the household members. All this information they will collect, and so that based on that information, and based on our age also, they will check whether we are in 20 to 30 years, or from 30 to 40 years, or 40 to 50 years. Based on that age bracket also, they will suggest us what type of premium uh, we need to take. Okay, so these are very good unsupervised learning examples. These are generic examples. So with this background, we will move to this applications. Okay, before going into that, there is one more topic that is called clustering. Okay, clustering is where the patterns of these multiple small unlabeled data can be put together. Okay, and we can draw one label to it. Okay, we can for example, if we look into that squares boxes of square shaped toys, or the cube shaped toys, we, by looking at one small cube, we can tell this is a cube. Okay, similarly, by making them into the multiple clusters, and we, if we investigate in detail, then we can name them. So that is how this clustering works. There are few examples, like in shopping malls we have the cluster of t-shirts, and there is one group of section that contains only the trousers. And in uh, in the fruits shop, we can observe this apples put together, and the bananas, mangoes put together. So this is also called the clustering. Okay, these are very good examples for this unsupervised learning. So, however, I didn't cover much in algorithm part, but I will show you how to apply our real data, or lab developed generated data, or literature generated data by using this machine learning tools. How can we develop one accurate model? Okay, so the first case study which I'm going to show now is the chemical guided screening of top performing metal organic frameworks for hydrogen storage. Yeah, so in general, the hydrogen energy is one of the alternative to the fossil fuels nowadays, because of its low energy density by weight, and high calorific value. Okay, so here you can see what is the energy consumption all around the world. Although this data is old, from 2019, however, most of the energy that we are consuming are from fossil fuels. Okay, to reduce this emissions, fossil fuel carbon emissions, we are trying to switch our fuels to the renewable energy based fuels. Hydrogen is one of them. The main reason behind picking hydrogen is we can get 3 times more energy density by weight to our current gasoline by using this hydrogen as a fuel. So, and on top of that, the emissions of the hydrogen are clean, and hydrogen availability is it is very abundant all around the world. Okay, by using this water splitting techniques, we can produce the hydrogen. And fuel cell vehicles and the power generation, such as the power plants, are slowly switching to this hydrogen based fuels. Then what is the problem? Why we are not using this hydrogen in in automobiles or in industries? The main problem with this hydrogen application is the storage. The storage, in the sense, hydrogen is in the gas phase at the room temperature. That means it is highly diffusive, and when we store the small amount of the hydrogen, you need large volumes of the tanks, which we cannot carry in our automobiles. So what we are doing is, we are trying to compress the hydrogen at very high pressures up to 400 bar. That means 400 times the pressure that from the atmospheric pressure, we are increasing it to the 400 bars and putting them in the cylinders and using in the automobiles, which is absolutely not safe for the road transport. And there are few other conventional techniques, like liquefying the hydrogen at 20 Kelvin. We can store the hydrogen. However, it requires super insulated tanks that consume this lot of energy for liquefaction and also the insulation. So the
Sir,
researchers, yes, please.
what about converting into to a urea and converting later into by Haber process into hydrogen?
Yes, that is also possible.
Okay. Is it recommended?
No, currently the research is going on, so I cannot comment on whether it is recommended at present or not. But yeah, green ammonia is one of the interesting research topic that people have been exploring. Yeah.
Okay. Okay.
So this storage of the hydrogen can be done by some new other techniques like one of the chemical engineering technique, that is adsorption, and storing this hydrogen inside the material in the metal hydrates, and there are chemical hydrates. So compared to the metal hydrates and the chemical hydrates, the regeneration of the hydrogen would be easy in case of adsorption. That means once the gas is adsorbed on the surface, adsorption means the gas molecule that will stick to the surface, such as the dust uh, that is adsorbed on the surface of our tables or on the surfaces. Okay. However, this at the time of removing this hydrogen, the energy required to remove is very low. That is the reason adsorption is preferred over the hydrate based techniques. And at the same time, this hydrogen can be stored in the same volume that we are using, the tanks we are using in the automobiles, with the same quantity but at low pressure. It won't be at the 400 bar pressure, it will be at 20 bar or less than that. Okay, that is possible. We can reduce the pressure if we are using this particular technique. So there are two performance metrics that are very important in understanding this technique, that is gravimetric storage capacity and the volumetric storage capacity. Okay, gravimetric storage capacity means how much amount of the hydrogen that you are storing in one system, one tank, and volumetric storage capacity means how much amount of the hydrogen that we are storing in the volume of that system. So why I am explaining this technical detail, so that you will understand why the input information and the features, how the features are very important in modeling, how they are important in machine learning model. Okay, the adsorption is nothing but, for example, there is one material here, adsorbent. This is a porous adsorbent material. So the gas molecule, the hydrogen will come and sit on the surface like this. For example, this is a monolayer. Because of single layer, there is a multi-layer adsorption. So in our labs, in our research labs, we synthesize this advanced adsorbent materials such as metal organic frameworks. These are the two materials which synthesized in our lab. These material have very good and very high storage capacities of hydrogen. So these materials, how to select these materials? So there are few properties like surface area, whether the surface, how much surface that is available for the hydrogen, and this is a porous material. This material looks like a sponge where there are holes inside it, where the gas molecule will diffuse through and adsorb on the surface. And at the same time, the density of this material is very low, and there is a pore size. This means whatever the opening you see over here, this is a pore entrance. So all these properties are very important physical properties of a material. Okay, for a high gas adsorption capacity. So here you can see this is called adsorption isotherm. With increase in the pressure, adsorption uptake is increasing. This is the behavior of gas adsorption. There are few favorable plots here, and strongly favorable, linear, and unfavorable and irreversible. So this favorable and unfavorability of gas adsorbing on the surface or gas storing inside this tank is actually depending on whether the adsorbent have some charge. That means degree of unsaturation, in the sense there is some negative charge that could attract the hydrogen molecule, or there is affinity between the gas, the hydrogen molecule, to the surface, and are there any metals or the linkers we have been using, are any metals. This metal organic frameworks are built based on metal oxides and organic linkers. That's why this particular property, the chemical property, is very important in modeling this system. So if you see this, multiple length scales are involved in this particular hydrogen storage tank. Okay, starting from the molecular level, how this gas molecule is coming and sitting on the surface, and how it is diffusing through and through these pellets and absorbing on the surface. So from small particle size to the adsorber level, there are multiple properties we need to consider in estimating or modeling this hydrogen storage tank. So the property, now based on this, what is the output properties we need to consider in this system? The output properties are gravimetric storage capacity. Department of Energy from US, they always gave this performance metrics such as gravimetric storage capacity and volumetric storage capacity as the benchmark to this hydrogen storage. So those are the output features we consider in this model. So now, based on this information of this hydrogen storage tank, we started working on building one machine learning model. So here you can see this workflow with 4 different steps. The first step is data preparation. There are a lot of databases available for this adsorbent material. There are around 4 lakh 12,000 metal organic frameworks database was available in the internet. So what we did couple of molecular simulations, and we generated gravimetric and volumetric storage capacities of the hydrogen, and also we calculated physical and the chemical properties of these metal organic frameworks. Why we are calling this as hybrid data? Because independent investigation of the physical characteristics or the chemical characteristics have been done so far. This is the first study which compared and which added both physical and the chemical effects on the system. That helped in predicting one of the best material in the literature. That is followed by we conducted 2 case studies here. One is pressure swing adsorption, another one is temperature pressure swing adsorption. That is very helpful in finding out how much amount of the hydrogen that is collected at the end of the process. So once the data has been generated, next step, as I mentioned previously, pre-processing and analysis has been done. So the data, we always separate them into the seen and unseen data. That means the seen information is what we use for training. Okay, unseen information is we use for the testing. So highly recommended our most widely used ratio is 70% and the 30%. So this 70% information is used to train different types of models here. Okay, that information is later studied by using this, tested by using unseen information. Okay, that helped us in predicting one of the best metal organic framework. Okay, the final step is validation. So once the top performing material has been discovered, we can either conduct the experimental study or the theoretical investigation. So independently, one theoretical investigation we can conduct. Here we have done one molecular simulation study to find out whether the machine learning model is working well or not. So this is a simple 4-step study, okay, which starts with the data preparation and data analysis, okay, then model development and application of a model by testing, then validation. Okay, these are the 4 important steps in application of any data to the energy systems. So here this is the high throughput screening workflow, where MOF database is first analyzed, data pre-processed here, and then we checked whether there is some missing information or not. Then we standardized the information. Then the screening has been done. That means out of those 4 lakh 12,000 metal organic frameworks, based on the performance metrics, that is whether the hydrogen capacity is high or low. If it is very high, then we will pick that MOF as one of the best candidate. Okay, that is called the high throughput screening. So this is you see in most of the machine learning papers, this is called Pearson correlation coefficient study. Okay, this is actually helpful in understanding how one feature are one input parameter that would affect the final output parameters. Okay, for example, if we closely observe, the UZ and UV are the output features, that is ultimate gravimetric and ultimate volumetric capacities, and at PV the pore volume is high. Okay, whenever there is a pore volume very high, okay, we see this UZ value, okay, the 0.91 UZ value, and also when the density relation with UZ, this is at negative correlation, that means the effect is reverse. Okay, if there is very good pore volume, that means more surface area and more void that is available for the hydrogen to absorb. So there is a physical relation that we can use to connect it. Okay, similarly this has been done for pressure swing and also for the temperature swing. So there are multiple models we have tried. Few of them are machine learning, and few of them, there is one deep learning model also we tried. There is a deep neural network and convolutional neural network models and gradient boosting, XGBoost and random forest. So there are few advanced models and conventional models we tried. ADCC is one of the deep learning model where we observed very good R square. So this mean square error, mean absolute error, and R square are the terms that you see mostly in this machine learning to compare how one model is more accurate than the other model. In this case, what is the interesting result we observed is when we consider only the only physical features and only the chemical features, okay, the comparison shows that by considering the chemical features, we observe the better accuracy. Okay, that means more information that we are providing from the chemical affinity point of view to the model, that improves the accuracy. So this is one of the
that is the chemical accuracy of the compound, that is MOF, that you are mentioning right now.
yes, yeah.
Okay, thank you.
So there is one more topic called shape analysis. This helps us in understanding whether, for example, the spam and no spam example which I have given, in most of the cases our ML models tells us whether the email is spam or not, but it would not tell us whether why we are putting that mail into the spam folder or not. Okay, there should be some reason for putting it. So this actually helps us in understanding why, when a model tells us whether this particular machine learning model telling that MOF is the best candidate for the hydrogen storage or not. So this shape analysis tells us whether the metallic percent is one of the feature, and also here void fraction is another feature. Based on this analysis, it tells whether if void fraction is very high, okay, then there are more amount of the gas molecule will come and store inside the pores. That means the more adsorption capacity is observed. So there is a physical relation. Otherwise, if, there is a notion saying that ML models are black box models. That means there is no physical information that we get so that we can relate and explain why that behavior is like that. Okay, that is the reason we do some interpretability study. This shape analysis or the global interpretability study actually helps us in finding which feature affects more, okay, on the final output. Here we can see the void fraction effect is more on PS, that is a pressure swing, and here also we can see PV, pore volume effect is more for the TPS. Okay. So at the end, there is a screening study we had done. Okay, this is a result for UZ and UV. Out of this 4,12,349 MOFs, we use that ADCC model to predict the output or UV values, and it compared with the UZ. Okay, UZ means gravimetric weight capacity and UV is the volumetric weight capacity. So the maximum and the mean observed are we can note here very high volumetric capacity of around 39.43 that is observed. Sorry, here we can observe that, and also there is 41.76 gravimetric capacity that is obtained. So here we have a benchmark from DOE, and at the same time there is targets, like ultimate targets. Whatever these red lines you see over here, these are the targets. Based on our targets, we found what are the materials which are more than or which they reached the benchmarks. These are the few MOFs noted here, such as EF, AYIU. This is called Cambridge Structural Database Code. Okay, that code we use to represent particular material. Here we obtained around 51 grams per liter of volumetric capacity, and also around 11.7 of ultimate gravimetric capacity of this particular material for temperature pressure swing. Similarly, for this material of pressure swing for XAHQA is the code that adsorbent named. Okay, that is that obtained as a very high gravimetric capacity of the 17, and also the volumetric storage capacity of 36. So as I mentioned, the validation is also as important as the conducting or building the model, since unless you validate your model, you are not confident enough to recommend it for the further applications. So what we did here is we conducted a couple of molecular simulations to check whether our result is correct or not. So this is a tool which is available. This is an open source tool called RASPA we have used for grand canonical Monte Carlo simulations, that gives us the adsorption isotherms as shown here. The difference in adsorption isotherm is nothing but the volumetric adsorption capacity and the gravimetric adsorption capacity. So that we compared our experimental results with, the molecular simulation results with the machine learning results, which were closely matching. Okay, for example, here GCMC gives 18.98%, and it is ADCC, the machine learning model, shown around 17.17. So coming to this conclusion of this particular work, this is mostly the aim of this work in the case study 1, that is how to use ML, machine learning models, to discover the material, that is a material discovery for the hydrogen storage. So we ended up discovering two materials. One is for pressure swing, another one is for temperature swing. The pressure swing this is material called XAHQA, with very high adsorption storage capacities. And for temperature pressure swing, these are the new materials which haven't been discovered before for this hydrogen application. Okay, so that is one of the interesting work we conducted by utilizing this machine learning. So this shows what is the capacity of this ML modeling when you have large data sets like this. Similarly, there is one more interesting topic I would like to show quickly within the few minutes maybe. So that is called
Sir, I have one question.
Sure, please.
Right now, the adsorption is done of the hydrogen, and rather than going for the liquefaction or other methods, high pressure storage, this could be one of the way that can be adopted. But just as a interesting query, I ask, how will you, since I do not know about this, how will you retrieve back the hydrogen that is already adsorbed in your material?
Yes, thanks for the question. It is very interesting question, but this behavior we generally observe in our regular lives. Okay, in our kitchen we have these gas cylinders, right? LPG cylinders. Okay, when we release that regulator, the gas will come out. That is coming out because the pressure inside the cylinder is high than the outside pressure. Okay, that is a pressure difference. Similarly, when we are storing the hydrogen inside this cylinder, the pressure will be at 20 bar or more than that. Okay, and outside pressure is 1 bar. So till it reaches that pressure, the whole hydrogen will come out. Is it clear?
Yes, sir. Yes, sir. Henry's law, something.
So in moving to this next topic, that is biomass pyrolysis, there are multiple examples, but we picked this system to understand how much bio oil that could be produced by pyrolysis. So the people who are aware of this particular operation, pyrolysis is nothing but the combustion of material in the absence of this oxygen. Okay, so there are various waste material available around. Okay, it could be municipal solid waste, animal residues, industrial residue, forest crops, sea waste, and agricultural crops. So whenever we have this carbon and the hydrogen that is present in these materials, that could be converted into the useful fuels, since it is a waste. So pyrolysis is one of the best technique, thermochemical technique, that can give us various fuels like biogas we will get, and bio oil we will get, and biochar we will get. Biogas is again used for fuel, and bio oil also can be used in industries. Then biochar has multiple applications like adsorbent. In the previous case I have shown, these also can be used as adsorbent. So there are multiple agricultural waste around us in India that could be converted into the useful fuels. So that is whole motivation behind it. Now the question is, what is the necessity in utilizing the ML, the machine learning, in this particular case? So this whole pyrolysis is very complex process, such as because what involves during this production of these biofuels is application of this high temperatures and absence of this oxygen. Because of during this procedure there are multiple reaction steps it will go through. So there are pyrolysis conditions like temperature, heating rate, particle size, and the nitrogen that is used as an inert atmosphere, and also the properties of the feedstock. That means what type of biomass waste you are considering, like what is the carbon content, hydrogen content, nitrogen and oxygen that has been present in that particular material, and how much of ash it is producing, and ash it may produce, and fixed carbon present in this, and what is the volatile matter. All those various compositions and also operating conditions that play a major role in predicting how much amount of the bio oil that is producing. So when there are multiple parameter effects on the final product, okay, tuning this each variable and conducting the experiments multiple times is very difficult. That's why machine learning can help us in this aspect by developing one of the best model, taking all these as an input features to predict the bio oil yield, okay, is one of the best alternative instead of going for the experiments. So again, the steps that are used in this particular method are same, starting with the data set collection. In this case, our data set size is pretty low. It is around 300 data points. Those data points are collected from the literature where they had done experiments previously, so that the data is reliable. Then we did some data processing, like removing outliers and all. Then we picked a couple of ML models that have been used in the literature previously, and which might be better fit for this kind of data. And also then we used some section of data set for the testing. Okay, that is followed by feature importance test, whether there is a way, what is the important features that are present in the given data set or not. Again, there is a correlation. Based on correlation, we can see over here what are the very good parameters that would affect the oil yield. Okay, and there are some positive correlations like hydrogen content. When there is more hydrogen content, there is good oil yield is obtained, and also the heating rate. When increasing the heating rate, there are chances of getting this more oil, and the reaction temperature. Similarly, there is a nitrogen content. We don't want nitrogen present in this feedstock, that may reduce the oil yield. So this analysis is information is very useful in selecting what type of feedstock. And similarly, there are this is actually a data analysis step where we find what is the maximum and minimum and outlier values that are present. These are the violin plots. And here you can see what are the various models like AdaBoost and artificial neural network, CataBoost models, multiple models we tried. CataBoost we found to be best fit for this setup. okay, such as training gave around 99 and testing shown around 93.2%. Then followed by there are few other models like XGBoost and Light Boost models we tried. So again, here in this shape analysis, this is a interpretability study that helped us in understanding whether which parameter is affecting much. Okay, like hydrogen content is very good feature that is very important in finding the bio-oil yield, and also followed by ash content, fixed carbon content, heating rate. So there is a one-way partial dependency plots also we can find from this information, such as how when we change the hydrogen content, how the bio-oil yield is changing, how the prediction of this bio-oil yield, it is reducing. And similarly, in the fixed carbon is increasing, at some point it raised the bio-oil yield and later it reduced, because there is one more reaction, it is reaction step that can cause the production of the char that would reduce the bio-oil yield. Okay, that is the behavior of this reaction temperature and fixed carbon content. So coming to conclusion of this part of the work, this work we tried multiple models to predict the bio-oil yield. That is very useful for most of the industries who would like to try different types of feedstocks, although they have ultimate and proximate analysis information. Based on this model, they will we can tell what is the bio-oil yield. So, however, this is again limited to the agricultural waste, since whatever agricultural waste we consider, that information only it can predict. It is not applicable for plastic pyrolysis, or it is not applicable for some other set of data. So we used some extreme gradient boost models, and also where accurate data can be predicted, for example R square up to 0.932. And there is a feature importance study which helped us in understanding which feature is more important in prediction of this bio-oil yield. So now coming to this conclusion of this whole talk, what I'm trying to say here is, although there are multiple techniques, fundamental techniques are available. It could be experimental techniques or theoretical techniques we have. This machine learning is currently trending because it has a capacity of adapting and for various engineering systems, like the chemical engineering system examples which I have shown. We adapted this for both experimental studies and also for theoretical studies. The first case, it was molecular simulation data that we generated. In second case, we used experimental data to generate it. Similarly, there are few other systems also we can apply this particular study. Currently, we are doing this for carbon capture and utilization. And also it can be applicable for hydrogen generation and production and utilization systems also. And similarly, data driven material design. So MOF discovery is one of the material discovery by AIML. That is one of the interesting studies. Similarly, there are multiple catalysts most of the people here might need. Okay, they can also utilize this technique for battery management systems, charging infrastructure, biomass and bioenergy, feed optimization. Okay, so all those various systems, there is no limit of for this AIML to apply for this various engineering systems. So these are very few examples I can give here. You can apply this for other systems based on the data that is available. So I would like to conclude this talk, and there I have been working at multiple institutes, starting with IIT Madras and University of Liverpool, and currently I'm at Indian Institute of Petroleum and Energy. So I would like to thank the support from these institutes, and once again I would like to thank the coordinators of this ATAL faculty development program for inviting me to this talk. If you have any questions, then definitely you can ask me now. Yeah, please. I think I took more than 5 minutes more, right?
It's perfect actually, not more. More discussion will come.
Yeah.
We
The
started 3
discussions.
minutes late also, you can
Yes.
consider that. Yeah, so that's
Any
it.
questions
Participants, you
from
have can
participants?
shoot questions, yeah.
Okay, in case anyone would like to model or develop their own ML based models, they can always contact me for their research work. You can always drop me a mail. We will be available. Our research group is working on this various theoretical techniques and ML techniques here. You are always welcome.
Thank you. Participants, please check the chat box. Feedback link is given. So it's the same link. You can provide the feedback for the session. So, Avesh, you would like to summarize? Yeah. Thanks, Sridhar. It was nice, 2 case studies which you explained. So it was really informative. I hope participants will not only two case studies, you also extended it and you also showed where now you can apply with
Yeah.
respect to chemical engineering.
Yeah,
So
the
that's
session was
very informative.
arranged very nicely. I mean,
Very nice.
instead of going into the machine learning
Mhm.
algorithms, the application was focused more. Definitely, people might have definitely helped who are working in this area.
Good.
Thank you very much, Sridhar,
Yeah.
for your time and sharing
Thanks.
your experience and knowledge here.
Thank you. Thank you for both of you and the audience. Yeah.
Have a good day.
Thanks.
Yeah.
Yeah.
Thank you. Good
Thank
night.
you.
Yeah.
Have a good night.
I can leave, right?
Yeah,
Yes,
Sridhar.